All right. So, physicists, we are going to go ahead and get started here. We are going to start with a check-in of the calendar. We're going to finish gravity and electricity today, and we're going to maybe do a lab simulation. We'll see. I was having technical issues with it earlier today, but we'll see if we can get it fixed. All right. Let me hop on Canvas here so that you can see what the calendar looks like. Maybe go team. All right. So, friends, I'd love you to have your attention up here. Please stop chatting with each other and listen, because the time is of the essence. Let's put it that way. Okay? Tuesday, Wednesday, Thursday, Friday. Last week we talked about gravity and electrostatics. Today we're going to finish up with electric fields. We may or may not do this, and if we don't, then I will send you the link so you can do it, because it's really fun, but I was having issues getting it to work. Anyway, so we'll get that done. Tomorrow we're going to talk a little bit about magnetism and how it relates to all of this business, and then Wednesday we are quizzing. So I want to make that really clear to you. Wednesday, and there's no wiggle room in this, friends. Wednesday we are quizzing over gravity and electricity and a little bit of magnetism. After that, we've got Thursday, Friday, Monday, Tuesday. Thursday, Friday, Monday, Tuesday, and then we have another quiz over circuits. Okay? And then we have a couple quick labs and a review, and then we've got our final. We've got a lot to do. It's going to happen really fast. So I want you to be aware. I know that it's a busy time of year. I totally get it. I know that AP tests are happening. I get it. I need you to give me as much of your full attention as possible. If you're going to be gone for an AP exam, I've looked, and I think that most of us are okay most of the time. But if you're going to be gone, you are still responsible for the material that's covered. Okay? If there's an assessment that you missed, then you need to make sure that you come talk to me so that we can get that figured out. Okay? This is a hard deadline for seniors, for sure. Okay? And this is a pretty hard deadline for everybody. So we're going to do some stuff after as well. Okay? We're getting into this point now where those 9 snow days, or however many it was, are kind of like we're really feeling it now. Where, if we had another week to kind of work through this stuff, we'd have a lot more wiggle room. But it is the way it is. Okay? What I would love to have your attention with right now is the gravity and electricity sheet that we started on Friday. So if you don't have that out yet, please pull that out. I think that everybody that wasn't here, you need one still? There should be one up here, I hope. Yep. Anybody else need one? You're welcome. All right. So part of the reason that I structured this set of notes this way was so that you could take a look at gravity and electricity side by side, literally, so you could kind of get an appreciation for some of the similarities and differences of the two. So before we move on, I just want you to take a look at these things. Raise your hand if you can tell me a similarity. What's something that's similar between gravity and electricity? Yeah, what's one? There are forces between two objects for both of them. And in fact, just to kind of make it a full conversation, any force is going to be a force between how many objects? 2. Yes. But in this case, they are both 2 objects. That's absolutely true. What's another thing you notice? Yeah?
The force decreases with distance.
Absolutely it does. And that is not trivial. That is not something that we need to take lightly. Both of them decrease with distance. And not only do both of them decrease with distance, they both decrease as the square of the distance increases. In fact, that is so interesting and so unique that we actually have a name for that. We're going to name this. These are both inverse square laws. If you're familiar with kind of modern physics and all of what they're trying to do, they're trying to put all of the forces together, right? There's this whole thing called the grand unified theory. It's something that a lot of physicists are working on, trying to put things together. Everything fits into a nice, neat package except this silly gravity thing. Gravity is the outlier. It's the weirdo. It's the thing that doesn't fit with the rest of the story. Scientists want it to fit so badly, and one of the big reasons is because these two forces look so darn similar. Do you see that? It's like it's got to work if it's that pretty, if it's that similar. All right, so that's two things. What else do you see? What else do you notice? Take a look. Don't wait for somebody else to talk. You look for something. What do you notice is the same? Yeah. How big they are? Yeah. Yeah, they both have constants. Absolutely, proportionality constants. It is interesting to note that the proportionality constant for gravitation is really, 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 really small, 10 to the negative 11th, right? Whereas the proportionality constant for electricity is really, 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 really big, 10 to the ninth, excuse me. So they both have proportionality constants, but they're very different in magnitude. Okay, tell me some differences or similarities if you still see some similarities. What else do you observe? I'm going to give you just a minute to talk to your table because I feel like I'm getting a couple tables that are participating and a couple tables that really are not. So talk to each other right now. I'm going to give you 35 seconds or something like that. Find two similarities or differences that have not yet been mentioned. Go, go, go. Talk to your tables. If you want to talk to these guys, you can. Or you can go over there. Whatever works. Once you have a conversation, though.
Jeez, Cara. You gotta listen. You don't have a choice.
Find some similarities or some differences. Either way, we're making observations about the world, right? All right. You know I'm going to call on your table first, right?
Yeah.
Okay, awesome. They're like, because she always does. What you got? What's something interesting that you found?
They both attract to something.
Yeah, they both have at least some attractive component, right? Gravity is always attractive, and electricity can be attractive, but the difference there is what? What's different in these cases? Yeah, one of them could be repulsive as well, right? So it's a difference that the electrostatic force or the electric force can be both attractive or repulsive, whereas the gravitational force is always attractive. Yeah. Other observations. What's another thing you found? Go, Zach.
The force between gravity, it's ones with mass, and for electricity, it's ones with charge.
Absolutely. We got ones with mass over here. This one's with charge. And this is not something we actually wrote down over here, but how many different kinds of mass are there? Not a trick question. Don't overthink it. One. Right? Mass is mass is mass is mass. Okay? Even antimatter, which is a thing, still has mass. And it's still the same mass, right? There isn't anti-mass. Mass is mass is mass. There's one kind. How many kinds of charges are there? Two. Don't overthink it again. Two. There are two kinds of charges and one kind of mass. All right. Other things that you observed that you want to say here before we move on? Anything else that you found? Similarities or differences? All right. Those are the big ones. I want you to be able to be appreciative of those things. Be able to calculate things, obviously, but also be able to describe things. Yeah.
So for like the force depends on more of whatever the force is. Because like with the two object with charge, the more charge there was more mass.
Awesome. So I'm going to just say that again to make sure that we all hear that and make sure that I'm saying what you said correctly. Does that make sense? So let me know. So in the gravitation, the objects that it deals with are objects with mass, and the more the mass, the bigger the force. In an electrostatic situation, the objects have to have charge. And what you're saying is that the bigger the charge, the bigger the force. Absolutely. So there's a similarity there as well. Yeah, nice parallelism. Yeah. All right. right. So on Friday, we started looking at this new thing, this new idea called a field. We said that a field describes the motion of a test object in the presence of this thing we call a field force. So a field force is a non-contact force. So if I go up and I tap somebody, that's a contact force, right? I'm going to tap somebody, it's contact force. We're talking about now things that are non-contact forces. Non-contact forces like gravity, it pulls things down without any sort of anything touching, no strings or pulling or pushing, okay? We said that with a flat earth, it pulls straight down. So we take my frog and we drop him here, he falls down, drop him here, he falls down, drop him here, he falls down. The conversation's got to stop. So if you need to move so that you're paying attention, then do, okay? Otherwise, turn around and pay attention up here, okay? My patience is gone right now. Thanks. All right. We okay here? On this one, all we did was zoom out, so now we got an earth that's actually round. And now I'm going to drop the frog from up top or down below or wherever. It's always pointing towards the center. Okay? Before we get down into this, I want to do the electrostatic situation. Let's compare. If I've got a little positive test charge, or excuse me, a positive charge here, when we had the gravitation thing, I took a little test mass. That was my frog. I want a little test charge. One thing to note, because otherwise people could decide different things and then we get different results. Somebody at some point said, okay, friends, we've all got to agree, and we are all going to make our test charges positive. From here on out, anytime we talk about a test charge, it will be positive. Okay? So now we're gonna ask the question, if I put a little positive test charge right here where that green dot is that little test charge going to be attracted to this big positive, or is it going to be repelled from the big positive? Repelled, does that make sense to you? Like charges repel, don't they? So that means that it's going to go in that direction. If I put it over here, where is it going to go? Towards or away? That's a good way to ask. Away. Oh my goodness, come on, thing. Right here, it's going to go away. It's going to go away, away, away. Okay. The field lines, just like they do with the gravity, the field lines show the direction of motion for a test charge. Field lines show a direction of motion for a positive, in this case, test charge. So that's what our positive charge would look like, because the force, as you've told me, is always going to be repulsive between two positively charged objects. Now, there are two boxes, not on accident. If I have a negative charge, what are those field lines going to look like? Think about the question. What's going to happen to a positive test charge if it's set somewhere just outside that negative charge? Are they going to be attractive or repulsive? It's going to be an attractive force, isn't it? I saw some people doing this. Yeah, they're all going to go in toward the center. Does this picture look similar to anything else that you've already drawn? Yes. Just like this one, doesn't it? The negative charge with its electric field lines around it look very, very similar to the gravitational field lines of Earth when it's zoomed way out. Okay? In fact, the picture is the same. So again, we've got the field lines point in toward a negative charge, and field lines point out away from a positive charge. Okay. How are we doing? Are we okay? Is that making sense? I'm going to do things in a bit of a different order than I had initially anticipated because I feel like it makes sense to move right from here to the back of your paper. So we'll come back and finish the front of your paper in a moment, but go ahead and trim it to the back. Okay? I've got some pictures there on the back for you. One charge is fun. Multiple charges is even more fun. So let's take a look, first of all, at this single point charge. So I left some space there for you to write some things. I'm going to write some things. We'll all write some things together. Okay? First of all, what kind of charge is that? Positive or negative? Positive. It's marked with a positive charge, right? Positive sign. And which way are those little arrows going? Away. They're going away because any little positive test charge that I place, like here, the charge is going to go that way. It's going to feel a force that's going to push it that way. Does that make sense? It's going to feel a force that would push it this way. Okay? So the thing that you might want to write down here is that lines, actually, I'm going to write this more officially. I apologize. Change of words here. We'll say the electric field lines. Okay? Always begin on positive test charges or on positive charges. Okay? And point away. Okay? We'll say on negative charges, the lines point in. I know we just wrote that down, but sometimes writing it down a couple of times and internalizing it a couple of times is helpful, especially with new content, new things that you're not super familiar with. Okay. You'll notice that on a single test charge that the lines are drawn symmetrically. Again, that geometry stuff coming back in, right? Symmetrically just means that they're all spread out all the way around. Okay? And on a quiz or a test, you might have the opportunity to draw electric field lines. If you do, this is just kind of a note. And the note would be that you need at least 6 E field lines from a single charge. I wish I could write better. There we go. Okay. One charge is fun. 2 charges is amazing. It's going to be wild and crazy. Are you ready? Here we go. If you have 2 like charges, what do you notice? Looks a little funny, right?
Yeah.
It looks a little funny. Tell me what it looks like. How does it look different from the single charge that you looked at it before?
There's none going towards the middle.
There are none going towards the middle, right? Nothing is going toward the middle. Again, the game is, where would that positive test charge go? Where would that positive test charge go? Let me put a positive test charge right over here. You might want to do the same thing, just so you can kind of think about it and remember where we're at. If I have a positive test charge here, is it going to feel a force from this plus 3? Is it going to be an attractive force or a repulsive force? Repulsive means it's going to push that it's going to push the test charge in this direction. But there's another charge over here, isn't there? is the one on the left side going to cause a positive, or excuse me, a attractive or repulsive force to that test charge? Repulsive as well. Question. Which force is going to be bigger? Let me label them. I'll call this one A and this one B. Which one is going to push harder on my positive test charge?
B,
Why do you say?
because it's shorter distance.
Shorter distance, right? Do you remember KQQ over R squared? The bigger the distance, the smaller the force. This is a much bigger distance to A than it is to B. So the force it feels from A is going to be pretty small. So it's going to be mostly in this direction, which is why the line goes in the way it does. But as it gets further and further along, it's going to get further from B and closer to A, and eventually it's just going to feel a force that takes it all the way this way. Does that make sense? Okay, so it's feeling forces from both of them and has to react to both of them together. The kind of cool thing that happens here is that the electric field lines represent a path for a positive test charge. So if you follow that electric field line, that is exactly the path that a positive test charge placed on that line would follow. So we got these funny curved lines. Question: what would happen to a positive test charge if I placed it right here? Right in the middle there? It feels a force from A, diagonal, right? And it feels a force from B, diagonal. The left and right parts of that are kind of like tug of war. But where does it definitely feel a force? Up. So there'd be an electric field line that's not really drawn here, but goes like this, right? What about if I put a positive test charge right here, down right at the bottom? It's going to go down. What if I put a test charge right in the middle? Exactly in the middle between A and B.
Stay there.
Does that kind of make sense? That's like the epitome of the tug of war, right? No, go that way. No, go that way. No, right? That's what's going to happen. And right at that moment there, it would just stop. Okay? Yeah. So it's just kind of interesting. It could, yeah. And in fact, there are ways that so there's a lot of physics that's tied up in all of this, right? If you have a bunch of charges, positive charges here, and you have negative, like you can actually get charges to suspend between them. That's how capacitors work. That's how cathode ray tubes work, like the old big TV sets. When you had electron beams going, that's exactly what they would do. Yeah. So that happens a lot, actually, is the short answer. This is kind of a theoretical picture, but yes, it does happen. So that's two like charges. Take a look at two opposite charges. What do you notice in this case? Does it look the same, or does it look a little different from the other one?
Different.
Indeed, it's different. At your tables right now, I want you to make some observations. What do you see that's different between the one above it and this one? Take a look and discuss. Go. Sorry. You'll remember it now, though, right? Hopefully not in your dreams, though. What's up, friend? Sure.
So it's
Whatever is closer.
getting attracted.
Whatever is closer to it, we'll just put it out.
Yeah, but the arrows would be the other direction.
Yes.
No, I think it did work.
So what if it's here then?
Inspired by.
Where are the arrows? Wait, what are the
It's
arrows?
here. Is there?
You should know that. Yeah.
So like never going down.
Oh,
So it actually oscillates back and forth, back and forth. It'd be like this
I would
motion.
actually.
Oh, it's not.
Kindness, education, and diversity.
Would it just sit here?
No, because it has momentum, right?
So no one's taking
It'd be like some kind of motion. The arrows tell the direction that a positive test charge would be. So if you look, they all are. That's what we said. We just said that. So if you look just like this one here, they're all positive.
First one no was saying
Because it's negative charge. So I put a positive charge here.
So what are they?
What are the what? Are the arrows? It's called electric field line.
I was at.
So they're like the little road maps to
Was
the positive
it
charges.
west?
They don't, like, do they actually exist? I mean, there aren't like lines going down in Gravity Island, but it's the same kind of idea. Does that help a little bit?
Yeah.
Okay, that's a good question.
Okay, literally.
All right, my friends. Really quickly before we answer this question, I want to go back up here because I had a really good question that was just asked. The question was, can you draw two like charges that are both negative? Yeah, you could. It's going to look very similar to this, except what? Arrows are going to go the other direction, right? Yeah, they're going to go the other direction. All right, let's look at these opposite charges. Tell me what you observed. I heard some good conversation. Zach, what do you got?
One from the charges from the positive one right in the negative.
Yeah, so if I put a charge right here, it's going to feel a force away from this charge. I'm going to label these again. We'll call them C and D this time, just so we don't get confused. If I've got a charge that's sitting, a positive test charge sitting very close to D, it's going to feel a push away from D, and at the same moment, it's going to feel a force towards C. So it's like a double boost, right? It's going to go that way. But it gets a little bit funny here. What if I put that positive test charge here? Now, it's much closer to D than it is to C. It's being repelled more from D than it is being attracted to C. Are you with me there? So it's going to feel a force away, but eventually as it goes down there, when it's here, it's now, now I'm getting closer, right? And that's why it's going to follow that path. It's going to follow that path. Yeah, go ahead.
You said like the test charges is always positive, but are there like in real life other actual ones that are going to the
So, okay, so it's a good question. It actually goes kind of, Lily was asking this question earlier too. So like, do these lines actually exist in real life? I mean, not really. Let me tell you what I mean by that. There are gravitational field lines that we would draw right here in this space. Do you see them? I don't see them. Okay? But physicists need a construct to be able to explain why this frog falls down. So that's what's going on. Now it's weird because there is no like negative mass, right? The reason that we have to then talk about a positive charge is because we always want the arrows, we want it to stay consistent. So that when you draw a field line diagram, and when Alec draws a field line diagram, and when Melissa draws a field line diagram, they all have to look the same. So that we're all talking about the same situation. Which is why we always say it's a positive test charge. Again, we shake our fists at Ben Franklin because he kind of screwed us up, right? The charges that actually move are not positive charges, are they? What kind of charges are actually doing the moving? Most of the time. Negative charges. And so a negative charge, and I don't want to confuse anybody, but I want to be real. If I put a negative charge, an electron, right here, where's it going to go? It's going to follow that red line backwards. Are you with me there? Okay. Ben Franklin had a 50-50 shot and he messed up. What are we going to do? I don't know. We're going to cry about it or we're just going to move on. Okay. But we are always going to talk about a positive test charge just so that I know that we're all talking with the same vocabulary. And even if I had decided, no, we're going to do a negative test charge, then when you went on to do something else and you happen to be talking to somebody about electric field lines in life, because I'm sure that will happen at some point, right? Then you would be backwards and everybody would be confused. And we don't want that. So all physicists everywhere have decided positive test charge done. Yeah. Okay. So I think we're kind of getting this, right? All of these lines are going to come around. All these lines are going to come around. So they all go to the negative. They go away from the positive. One observation here. Is it possible for electric field lines to cross? Is it possible for me to have an electric field line like this and then another one like this? Jacob, you had a 50-50 shot. Was that a guess or was that an assertive, we get it answer?
Good guess.
Okay. 50-50 shot. He said no. Anybody want to agree with him or disagree with him, but also provide some sort of evidence? In all of the pictures you have, do the field lines cross? No, they don't. We said just up here that electric field lines represent the path that the charge will take. If I have two field lines that cross, so I've got a test charge that's right here, and it's following this path, what would it mean if it passed through this point? And there were two field lines. What would that mean? What's that? So I'm saying, like, if these two charges were here, like the +3 and -3 were there, this little test charge moved along this, and it got to this point. Test charges are not sentient beings, but what's the situation?
It could go a different way.
It could go multiple ways. Does that make any sense? If you're just adding two forces, if I have a frog, and I have the earth, and I have clay, and I add up the force that the earth pulls on the frog, and the clay pulls on the frog, are there going to be multiple answers as to where the frog goes? No! There would never be. That doesn't make any sense because you're adding two things together, right? It doesn't make any sense. We can't have field lines crossing because that would tell us that there are two different ways that it could go. Not possible. We're going to make a note of that. Electric field lines cannot cross. It's not possible. It doesn't make sense for that to happen. Okay? It doesn't make sense. Okay? So Courtney was a little bit upset with me about this last picture I was gathering based on her comment while you guys were talking about the other one. Is that true? Gave you a little bit of a, huh? Because why? Looks like a spider. It kind of does. I apologize. But I know, right? That just kind of happened nicely. I think it also illustrates this point really well. Besides the fact that it looks like a spider, we're going to throw that one away. What else do you observe in this picture?
Weird.
Yes. Other people. What else do you observe? Yeah.
It's not like two opposite charges where most of them go straight towards the other charge. Most of them aren't going towards it. They're like, one of them isn't like strong enough to pull the rest of them towards it, basically.
Yeah. Go ahead, Shad.
The charges are opposite and unequal.
They're opposite. So it's similar in that way to this one. But unlike this one where it's +3, -3, they're different sizes, aren't they?
How are we supposed to know which one has a greater magnitude?
I would tell you.
Okay.
But you could also tell from this. I mean, it says, right, +2 and -1. This one has more lines, doesn't it? Yeah.
So for the last one, that actually corresponds to the -1. Almost out of, yeah.
That one?
Whereas like the one with the two opposite charges, it doesn't go past the point, the bottom line, it goes past it, it has to come back.
Mm-hmm. So let me ask a quick question here. This one here is pretty well zoomed in. Tell me, what is the net charge of this system?
0.
0. So if I zoom way out from this system, does it make sense that this line is actually going to come over here and connect? And that this one's going to come over here and connect? And if I zoom way out and I have a net charge of 0, there will actually be no electric field lines that come out of this system. Does that make sense? Because every single one of these is accounted with one of those. So they would go around and there would be nothing left. The net charge, I'm going to write this down because that's a good point. The net charge here is 0 coulombs. And as a result, try that again. Zoomed way out. No, I'm going to say extra electric field lines. Because every single one of them would connect to another. Is that true of the one down below?
No.
It is not. In fact, all of the electric field lines from this -1 are already taken care of, aren't they? Let's count up the electric field lines coming out of the -1. I've got 1, 2, 3, 4, 5, 6, 7. I've got 8 of them. Before thinking too hard about it, how many lines do I have coming out of the +2? You told me there were 8 legs on this spider, right? And I've got 8 there taken care of. Yeah, so let's count them up. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? So there are twice as many lines coming out of the +2 as there are going into the -1. There are twice as many lines coming out of the +2 as there are going into the -1. If I zoom out from this, what's it going to look like? What kind of charge? +1. If I zoom way out, the lines that go out are going to go radially outwards, just like this one. Okay? Let's write this down. The number of electric field lines is proportional to the magnitude of the charge. So I've got 16 lines coming out of the 2, and I've got 8 lines coming into the -1. Magnitude just means size, right? Doesn't matter if it's positive or negative. Okay? If you look at the 2 right above, the ones that are both positive and -3 are both +3s. They have the same number of lines because their magnitude of charges are all the same. Okay? So with this, on a quiz or a test or both, I could ask you to do a couple of things. I will ask you to do a couple of things. One option would be that I would say draw the electric field lines for 2 charges that are the same, 2 positive charges. Draw the electric field lines for 2 opposite charges. Draw the electric field lines for a positive and a negative that are the same size or different size. You with me there? Does that make sense? Okay? Or I could give you a picture like this without these and ask, are the charges positive or negative? And how do the sizes compare? Okay? Looking at the picture, you should be able to tell me if we've got positive or negative because the lines are going in or out. And you should be able to tell me the relative size based on the number of lines. Does that seem doable? There's at least one of those to practice on in your homework. Okay? Yeah, go ahead.
The two like charges, say one of them is 6 and the other one is 3.
Mm-hmm.
How could you tell whether it's like a 1 to 2?
Because there would only be a few of this one and a lot of this one, or vice versa. And so then this is actually going to end up spreading around. Does that make sense? Yeah. Yeah. So it wouldn't be symmetrical like this anymore. Okay. So that's a skill. I want to make sure you know how to do that one. We're going to hop back to the front of that sheet for just a couple moments here to talk about quantifying the electric field. So quantifying the gravitational field, we did this on Friday. Remember we said the force divided by the mass gave us gm over r squared. And at the very end of the period, I asked you to do a calculation for the Earth with the mass of the Earth and the radius of the Earth. And you found that the gravitational field of the Earth at the surface was 9.8, which is not a foreign number to you, is it? You've dealt with 9.8 a few times over the year. A few times. You know that the acceleration due to gravity at the surface of the Earth is 9.8 meters per second squared. Why am I going back to this? To remind you that I might ask a question on Wednesday that says, what would happen if the Earth was the same size as it was, but the density was twice as big? If it was twice as dense but the same size, tell me about the gravitational field strength. What would you tell me? If the density goes up, what does that mean? What is density? You remember? Anybody?
It's like the space in between like molecules.
Right. Yeah. The more dense you are, the more mass you have per volume. Yeah? Do we know this? More mass per volume. That means the radius is staying the same, but the mass goes up. If the radius stays the same, but the mass goes up, what happens to this quantity here? It gets bigger. If it gets bigger, that means that when I drop the frog, he's going to fall at a faster rate now. Okay? Because he's going to speed up faster for every second that he's falling. All right? So that's going to be one thing I want you to know. The other one that I want you to know is the electric field. That's what we're going to do right now. So just like we did with the other, we're going to take the electric field divided by, well, last time we divided by the mass, the test mass. What do you think we're going to divide by on this one? The charge, the little test charge, right? And the electric field strength is marked with the capital E. If we get rid of one of the test charges up in the force equation, we're left with K Q1 over R squared. And that right there is the electric field equation. We're going to try out a couple of questions right now, but I want to tell you right now so that you know, this equation is not on your equation sheet because when I made your equation sheet, I hadn't looked at the standards and what we had to cover. This one is on the list of things we need to cover. There will be questions like this on the quiz, but I will give you this equation on the quiz. Does that make sense to everybody? Okay? So no, I'm not trying to do anything mean or bad. I just don't want to have to print off new equation sheets for you for one equation. Okay? So that equation will be on the equation sheet. I want to look at the units of what this thing is going to be measured in. A force is measured in what units? Newtons. And charge is measured in coulombs. The electric field is measured in newtons per coulomb. The gravitational field, we wrote it as meters per second squared, but it actually can also be newtons per kilogram. It's the same thing. It all works itself out. Okay. I'm going to do a couple of practice problems. I don't think there is space on your paper to do this. You can certainly do them on the back or on separate paper. Either way, you will need a calculator out right now. We're going to do a couple quick questions. So make sure that you're with me here, friends. Example 1. I would like for you to calculate for me the electric field if you are a distance of 0.01 meters. Oops, that's really ugly. Away from a charge of 1.3 times 10 to the negative 9th coulombs. I would like for you to calculate for me the electric field if you're 0.01 meters away from a 1.3 times 10 to the negative 9th Coulomb charge. Okay, I'm going to give you just a minute or two to try that out. So the equation is right up here. K is 8.99 times 10 to the 9th. Okay. Go ahead and give that a shot. All right, how are we doing, team? Silent, but you got it, I'm hoping. So E equals KQ over R squared. What did we get for a value? Oh, it's frozen, I'm sorry. Boom. What did you get for an answer? I can't hear you, what? 1? Point what? Or 1 point nothing? Just the answer, was it just 1? I don't know. I don't have a calculator, so I'm not doing it. You tell me. What'd you get? Oh, so that's like 1.16 times 10 to the what? Well, you can count out. Count the zeros. Do you guys agree? 1.16 times 10 to the 5th? Yeah, scientific notation is your friend with this stuff, friends. I'm not saying you have to do it, but I'm saying I would strongly encourage you to do it. Fair? I'm not going to count it wrong if you do it right and you have it written out with tons of zeros. It just takes way more time and effort, in my opinion. All right, so that's the first one. The second one that I want you to do is a little bit different. There's a problem like this one on your homework for, I don't know, someday in this week or something like that. Situation is that you've got one charge here. I'm going to call it charge 1. You've got another charge here. I'm going to call it charge 2. They are nailed down, and they are a distance of 1 meter apart. I would like to know the electric field right in the middle. Okay? In the middle. Charge 1 has a charge of 1.6 times 10 to the 9th, or negative 9th, excuse me. Charge 2 has a charge of negative 2 times 10 to the negative 9th. And I would like to know the electric field total at that X. Now, before you go in too far by yourself, let me help you out for just a second. Let's think about this. What am I putting here if I've got an electric field? I'm putting a what kind of test charge?
Positive.
A positive test charge. A positive test charge, is that going to be attracted or repulsed from Q1? Repulsed. It's going to feel a push away, right? So E1 is going to go in this direction. Talk to me about relation to Q2.
Attracted.
It's going to be attracted to Q2. Are you with me there? So we're going to have E1 is pulling this way and E2 is also pulling that way. So the total is going to be E1 plus E2. You're going to add the values. You're going to add the magnitudes. The negatives and positives that exist here do not exist down here. You need to think about the pulling and pushing. That's what you're going for, okay? Give it a shot. Talk to each other. If you're stuck, get some help.